Okay, for our second talk for this session, we have Extending BAS for Improved New Product Forecasting, David Wu from Lehigh University and Carl Kempf from Intel Corporation.
Thank you. Good afternoon. My name's Carl Kempf. I'm here representing the Intel part of the team. David Wu will be presenting some of the mathematics, and he's representing the Lehigh University team. We have some copies of the paper up here if anybody's interested in it. We'll be presenting our improvements to BAS, extending BAS, in three parts. I'll start off by explaining the general business problem we're trying to solve. David will then take over and show the details of the extensions. I'll then come back and give you the results of applying the mathematics to real problems at Intel and show you the business impacts and then conclusions. The basic general business problem we're talking about is that, in my experience, predicting the future is probably the most difficult mathematics problem I work on, but in a big company, also a very important problem financially. This is especially true when you're introducing a new product into the market. Very important to have the right amount in the right place at the right time. If you have too little too late, you risk missing market acceptance of your product because you can't deliver it, and in the longer term, perhaps even lose market share. If you have too much or too early production of the new product, you've either used your capacity for the wrong thing. You could have used it to build something that you could sell, and at least you're going to pay an inventory holding cost. So solving this problem requires an understanding of the life cycle of your demand process, and also the utilization of every piece of information you can get from the market as soon as it becomes available. Diagrammatically, the problem we're talking about is a market on the right, an original equipment manufacturer who's making things that sell directly into the market, a supplier of components to that OEM. Both the supplier and the OEM have production capacity. In many cases, the OEM is using some contract manufacturer. Of course, over the course of time, both the OEM and the supplier are looking at the market, trying to understand how the new components from the supplier and the new product from the OEM are going to be received by the market. It's often the case that the supplier has to start raw materials into its production system, given that the OEM generally has a much shorter production cycle. Eventually, the OEM decides the orders and material flows through the system. We're particularly interested in the case that's the next level of complexity up from this, when in fact there are many markets. It could be one OEM supplying many markets or many OEMs supplying many markets. Now the interaction between the markets becomes quite an interesting proposition for the supplier. The important part to recognize in solving this complex problem is that at various stages in the life of the product, be it the component product or the OEM's final product, there are various stages. There's information that you can glean from the market pre-launch before you actually have the product for sale. You can get some idea of market sizes and cycle lengths from your previous adventures in the market. Also information from customers. Once the product is actually in the market, of course, you can look at early sales data, intelligence that's coming back from the field and from the market in general. Once the product starts to ramp down, of course, you're talking to your customers about their next project, about their next product. Field forecasts are updating, and finally, you get to end of life. The important solution to the problem is to figure out which of the curves you're actually going to be on. Again, too little, too late, risks market acceptance; too much, too early, potentially waste your capacity and causes you inventory holding costs. So I'll turn it over now to David, who will tell you about the mathematics we've been using to solve this problem by extending BAS.
Thank you, Carl. So when we started to look at this problem, we have decided this is actually a fairly generic problem in the industry in terms of the need to introduce a new product into the market and also have quick market access, and that basically goes in cycles. The reason we're interested in the Bass diffusion model is this is a model that has been used in various different industries. It started with to explain the technology diffusion process for durable goods. And turn out this is a model that's also very useful in describing various different kinds of models, from pharmaceutical to retail to consumer goods and so on. So we basically want to look at this problem as a generic problem, now not limited to Intel or, for that matter, semiconductor or high-tech, but for business in general. And so the best model basically, if you look at the curve down there, describe this diffusion process that starts with what Carl just mentioned, the initial ramp up, maturity, and ramp down. And if you take the integral of that curve and you end up with a cumulative demand, which is basically tells you at any particular point the percentage of life cycle demand that's been realized up to this point. And the good news is since we're looking at the future, these S-shaped curves, and that basically now in this case help us to describe what the life cycle of a product look like. And we actually know a whole lot about these S-shaped curves. And in the literature, there are something like 29, 30 of these different S-shaped curves that has been documented. And if you look at in the bottom of the slide there are some of the different families of these S-shaped curves. And the benefit of this is if you think about these curves as representing a particular way a product life cycle is going to unfold, each one of these curves actually give you a possible scenario of how that life cycle is likely to unfold over time. So instead of looking at an infinite number of futures, now you are boiling down to a finite number of possible patterns, if you will. So the idea is the approach we take is to take a catalog of these k different diffusion models and think about the universe as a convex combination of these k different diffusion models that capture basically the different vertical markets that we're trying to market our product to. So the process goes something like this. And remember now we have converted the problem of forecasting as a way of trying to decide which one of these curves actually describe the life cycle the best. So if we have some early sales data that early on in the life cycle, we can basically go through, we can use one of the diffusion model to do a nonlinear curve fitting, and to decide how good a fit is this early sales information fitting our particular diffusion model. And that gives us a basically distribution at the end, and the distribution is coming from really the random fitting error from the nonlinear curve fitting. So you have this distribution at the end that represents really the forecast error. Now imagine now if you, since there are many different diffusion models out there, and we're trying to make a convex combination of them, let's say in this example we use 3 diffusion models, not just Bass, but we can also use logistics or Weibull or and so on. And so each one of these diffusion models would give me a distribution. And since these distributions are basically random fitting error, they are actually independently distributed. So now I can, if I combine the prediction from all these different diffusion models in a certain way, and what happens is I can guarantee to reduce the forecast error as a result of it. How do I combine them? In short, the way I combine them is I put a weight. When I do my convex combination, the weight is inversely proportional to their forecast variance. In other words, for one that with a large variance, I give a smaller weight, and vice versa. So we have proved mathematically that if you do this, if you combine these models in a way that I'm describing, then you will always decrease the forecast variance by combining these various different models. And Carl later is going to talk about some empirical evidence that actually show us this is indeed the case. And the second part of the problem is now we have take care of the part that there are diverse market we're trying to predict. And the second is the fact that there are information that's available to us throughout the life cycle. The information is fast changing, and new information keep coming in. And to capture that, we introduce the concept of a demand leading indicator. And a narrow definition of a demand indicator is basically time series that in some ways predict the pattern of the future demand of our product in some ways. And the broad definition is basically any information that have some indication power, and I'll get into a little bit more examples in a minute. And so this leading indicator, in essence, tell you a little bit about what is coming, what is the trend, and what is the market condition, and what should you react to the changing market condition. And only have one requirement, which is this leading indicator has to be an unbiased estimate of the actual. So a lot of noise is okay, but the mean is centered at roughly the same place as the actual mean. And the good news is that you can verify this after the facts. And if your leading indicator is in fact biased, then over time you can unbias it. In other words, the longer you apply this approach, the learning will pick up, and we can take away the bias over time. And we can use multiple leading indicators, and we can combine them simultaneously or use various different ones of them over time. And some of the information bases, what are they coming from? They could be coming from the demand from related products. For example, the product that could be a particular computer chipset, and versus a CPU. So if you know what the chipset sales is like, and a couple of months later, you know that's going to have an impact to the CPU. Some of the advanced information that's offered by the customer, your customer tell you, you need to get ready for my new product, which has the following features, and those are leading indicators. And some of the early sales, as I mentioned, field forecasts, these field representative, and they stay very close to the customer, and they bring back some of these field intelligence, if you will, and that could be used as a leading indicator. Ramp down effect, if you have a previous generation of product that's ramping down, and by knowing roughly what the market size is, you take the market size and take down what is the remaining product from the previous generation still in the market, you get a leading indicator for the next generation, right? So that's a couple examples of how leading indicator could look like. And here's an example, and this is a field forecast that at Intel. And so if you look at the lighted blue one, the turquoise color, that's basically field intelligence 3 months ahead of a particular period of time, the demand. And the blue is 1 month ahead, and the pink there is what actually happened in shipment. So you can see that the pattern is actually emerging fairly early on, and you should use that information as leading indicator. So how do we do this mathematically? As I mentioned that whenever we have some early sales information, we can fit this curve, we end up with a distribution. This is something I showed you before. Now, if we put this in a Bayesian statistical framework, and what happened is if I have some leading indicator information, and what that does is it buy me some time. It buy me time L, if you will, into the future. Right? So I know something a little bit, maybe 3 months, maybe 6 months ahead of time. I'm going to throw this information into my initial estimation, and I perform an update, and this would on itself reduce the variance of my forecast. But better yet, if I take a large sample of leading indicators, and that basically forms a sampling distribution in the Bayesian framework. So each one of these leading indicators could project the future using the diffusion model I had before. All right, each one of them give me a normally distributed an IID set of distributions, and if I now combine them in the Bayesian framework, the posterior distribution I have at the end is basically guaranteed to have a smaller variance. Again, so now I again have a way of reducing the forecast error in a systematic way. So if you look at the equation down there, it basically says that through the Bayesian update, your posterior distribution is basically a weighted combination between your prior, what you know before, and your sampling distribution, what you learn from the leading indicators. And so happens also here, the weight you are assigning it is also inversely proportional to the variance of the sampling distribution. So it's actually two methods actually unified under the same framework. And the good news is that it doesn't really matter in what sequence or in what order or when you throw that information in. You can basically perform this update and the variance will reduce. So this is the second theoretical insight that we come up with. And again, we can prove mathematically that if you come up with a leading indicator and you make sure they're unbiased estimates, and the variance of the forecast will always decrease, it's guaranteed to decrease. Now, using these two fairly important mathematical insights, one is combining various different diffusion models, and each representing the dynamic from different vertical markets. So that's one dimension. And as we use k of them, k different diffusion models, and we use m leading indicators, the various different type of leading indicators. So we have k times m different potential updates that we can perform during the life cycle of the product, and both of them will guarantee to reduce the forecast variance. So this is a fairly generic approach that we could apply to many different settings. And Carl is now going to talk about the actual implementation we did at Intel.
On the off chance that somebody in the audience has never actually heard of Intel Corporation, we make microprocessors. We're the world's largest semiconductor manufacturer. We're very proud to have had 88 consecutive quarters of positive net income and to have been one of the top 10 most valuable brands in the world for 10 consecutive years. We have the problem we've been discussing. We make chips, we make wafers on the left, we saw them up and put them in packages on the right, we sell them to OEMs, many OEMs, in fact, many of whom you've heard of, who sell them in vertical order, the desktop market, the laptop market, and the server market. This is a big problem for us in the first case because of timing. The life cycle of products in the microprocessor industry is measured in quarters, usually between 3 quarters and 6 quarters. On the other hand, it takes us 3 months to manufacture a microprocessor. And of course, the market has day-to-day volatility. Our customers literally can change their orders until a very short time before we ship the material to them. So we have the need to capture the characteristics in multiple markets, server, desktop, and mobile to be specific. And given the day-to-day volatility of the market, we have a large inflow of information from the market. So the team from Intel and Lehigh has been collaborating on working this problem for the past few years. The standard process culminates in the last, the old process, if you like, culminates in the last week of the month. The forecasting team spends the first 3 weeks of the month collecting data. They actually generate the forecast in the last week of the month. They're generally forecasting the next 12 months, so it's an ongoing process every month, generating 12 months into the future for multiple families in each of the server and desktop and mobile markets. They use the ever-popular forecasting tool called Excel, using all the data they've collected and a lot of judgment. Takes in that last week, it takes a few dozen people to actually consolidate the information and generate the forecast. Our evaluation of these extensions to BAS were first implemented in what we call our planner's workbench. One of the first systems we implemented for the forecasters was simply a database and a GUI to do data mining so that they could collect all their information and look at it in a variety of ways. But we architected that system so that we could insert algorithms between the database and the GUI as we got better and better ideas on how to run this. We ran the mathematics that David has just described to you in parallel with the standard process. We've been doing that for 9 months. We started in December of 2008. Our management was happy to let us focus on desktop, which represent about 9 different product families, about a third of Intel's revenue. So we have data for that amount of time. David mentioned before the idea of combining many models. We used historical data for 60 of our products, 26 server products, 17 desktop families, and 17 mobile families historically. To fit the models, we picked the best 5 that are shown on the left, the average sum of squares error from what the model predicted versus what actually happened historically. The next to the last bar on the right shows the power of combining these models. The last bar on the right shows the fallacy of picking one model. These are all fits of 1 year of data. The bar on the right is what you would have gotten at the end of a year had at the 6-month point you picked the best model and continued on with it. So the combined, the idea of combining the models is quite powerful, keeps you from picking the wrong one. The other piece, of course, that we had to do was to select leading indicators to include in the model. And here are the ones that we've used so far. I need to explain design wins to you just a little bit. Our products are complicated enough that without an interaction with our customers, they have trouble designing their products. So it's not, it's fairly standard business that 12 to 18 months before we actually have product to ship to our customers, their engineers get together with our engineers and we start the collaborative design of the specification of our device, the printed circuit board, and the chassis that they're going to insert that device in. And as soon as we actually sign a contract that our engineers are going to spend time with each other, we have a design win. That design win generally includes when they think they're going to introduce their product into the market, what they think its lifetime will be, and roughly how many units. So we have an interesting way of debiasing these based on wisdom of crowds. We have a number of customers, a few hundred. Some of them are optimistic, some of them are pessimistic. We find that the design wins are a very good leading indicator. Of course, we have field sales folks who are located in buildings literally across the street from our customers. They're sending us information. Once we do start to get the product close to being fully functional, we're sending out samples to our customers. They're giving us feedback. Finally, chipsets, as David mentioned. It's not uncommon for our customers to buy the surrounding chips to test their printed circuit boards before they actually get the microprocessor that's the expensive component. And of course, once sales starts, we have a variety of sales data to work from. Design wins, here's one example of design wins as a leading indicator. And again, the debiasing has already taken place in that the design wins are already a combination of estimates from as many as 200 of our customers. Field forecasts are David showed you this plot before. The field is giving us forecasts of what's going to happen, sometimes on a bi-weekly basis, sometimes on a monthly basis, depending on how fast they're getting the data. Now, the way that we've used the forecast needs a little explanation. The standard forecasting process is to forecast 12 months out, a month at a time. But of course, that forecast has different pieces of it have different value to us. As I mentioned to you, our throughput time of our manufacturing system is about 3 months. So the forecast for the next 3 months, the material is already in the factory. We can use that information to prioritize some things, deprioritize things, make modifications as where we're intending to ship it. But in a sense, the bullet is already traveling down the barrel of the gun. You can re-aim a little bit. The month 5 through 12 forecast, again, given our 3-month manufacturing lead time, is very useful for planning, for being sure manufacturing's got the right capacity in the right place, getting the right materials available, planning logistics. But the important part of the forecast is the one for month 4. That's the forecast that we're actually starting material into the front end of our manufacturing line. So the material that I start today is going to be available on the first day of month 4. So this is the actual decision point. And again, if we start too much, we'll build inventory. We'll have to pay a holding cost. If we start too little, we'll incur an opportunity cost, unless there's some inventory to use from the previous period. So we've used those costs to estimate the value here as we switch from the old method to the new method. We have an inventory holding cost for each of the 9 product families. We have an opportunity cost for each of the 9 families. And we looked at, of course, at the forecast error. The forecast error for the 9 products that we've looked at this for, and again, we've looked at it for 9 months, 3-month manufacturing cycle usually takes a month or 2 for the accountants to actually give us the real data. So this is for 4 months towards the end of that 9 months. So far, we've seen a 33% reduction in forecast error. You'll notice, however, product 3 and product 9, the old method still works a little better. So we're looking over the shoulder of those folks to see what information are they using that we're not. So again, we took the forecast, the old forecast, the new forecast, did the calculations for manufacturing for each one based on the actuals. If the forecast made too much stuff, we charged it an inventory holding cost. If the forecast made too little, there was an opportunity cost unless there was some inventory from the previous period that could be used. So the comparing the 2 forecasts using that evaluation method, we see over the 9 products, which again is about a third of our overall product line for 4 months, third of a year, has generated roughly $12 million in savings, or our expectation as we spread this across the rest of our product lines and use it over the course of a year is more like $100 million a year. You'll see some interesting bars, however. Remember, 3 and 9 were the ones that the old forecasting method was better. On 4, we had a lower forecast error, but you see a lower valuation. This is because each of the products has a different inventory holding cost. Each of the products has a different opportunity loss. And depending on how the forecasts go dynamically, if you have a forecast that's too high in the first few periods, you have some inventory. If you go a little low over the next couple periods, you've got inventory to cover it. If you're a little low in the first place, you miss some demand. And if you're a little high in the second place, it's too late. You already missed it. Now you have an inventory holding cost. So straight point estimate of forecast error doesn't necessarily transfer into the dynamics of how much money you're making as you go along. But we're hopeful of a nice round $100 million a year as we proliferate this. So 3 future directions. Obviously, as I say, we've applied this to the desktop market, the server market, and the laptop market are next. As David indicated, adding leading indicators will help us here, and I'll show you an example of one. The other thing that's just occurred in the last couple months, in fact, after we wrote the paper, is that we've started to apply this Bayesian updating technique to other forecasting problems in the business. Here's kind of a fun example. I threw this in. We have lots of these as we go look for leading indicators. I threw this in because it's kind of a fun one. It turns out that Google keeps track of specific queries. And if you go look at queries for our specific products, this is for the gaming market, for the high-end desktop, that Google searches turn out to be a very good leading indicator for our high-end desktop sales into the gaming market. Who would have guessed? The problem, the additional business problem we're working on is the one that I spoke about this morning in another presentation. The fact that projects always tend to run long. It takes us about 18 months to go from the final design of a product until we've actually got volume silicon to ship to people. The first 9 months of that, the designers are laying out the circuits, positioning the transistors, connecting them, and doing what we call pre-silicon validation. They're validating the circuits are going to work with circuit simulators. In the last 9 months, We've actually gotten enough confidence in the design to turn it into silicon, and now they're doing post-silicon validation, testing the microprocessor to see that it's doing all the things that it's supposed to do. Interestingly enough, in both the pre-silicon and the post-silicon validations, we get weekly bug reports. What new bugs have popped up in the simulators? What new bugs have popped up in the silicon? How bad are they? Are they showstopper bugs? Are they medium bugs? Are they not so worrisome? And we get them every week. What new bugs have appeared? How are we doing on the ones that we found before? Which ones have we fixed? Turns out these are very good leading indicators as we look at the historical record, since we have lots of data of past bug reports and whether the product delivered on time, was delayed a few weeks, was delayed a few months. So we're looking into the possibility of taking the base distribution of how our projects usually deliver as the initial estimate, and then doing Bayesian updating as we get weekly reports on bugs. So, in conclusion, we think we have a general decision framework for new product introductions, for new product demand forecasting, based on that's particularly powerful in markets that have products that diffuse at a very high rate of speed. The diffusion model's been put on a much more comprehensive theoretical basis and improved by looking across different verticals with different models and combining them, and by looking at information from different stages. As David said, you weight the leading indicator. Obviously, once you're halfway through the sales cycle, the design wins are not such a good leading indicator anymore. So you can adjust the weights of the leading indicators as you go through the life cycle. This is a mathematical framework that perpetually reduces the forecast variance. And in application at Intel, we've seen an average reduction in forecast error of 33%, increase in financial benefit of roughly $12 million over a third of our line, over a third of a year. I failed to mention that, in fact, in that last week, it generally takes a few dozen people a few days to generate the forecast. With this technique, we generate the forecast in about 2 hours. So we're looking forward, as the methodology gets more and more acceptance by the forecasters, as they see more and more success of even more streamlining our business process. And as I say, we're adding leading indicators and thinking of applying the technique to other forecasting problems. And with that, I'll take questions. So the question is about using information from the OEMs as leading indicators and perhaps even collaborating with them. The brief answer, I've got a foil set on that. The brief answer is that our collaboration was interesting in that we were looking at design wins as a leading indicator on its own. David was developing the mathematics to combine leading indicators, so this was a match, a good match. Actually, I've got a separate paper on wisdom of crowds, the idea that if you get enough independent experts who give you an estimate, by combining them, you actually have a chance of dramatically reducing, if not eliminating, bias. And my example and the paper is about using these design wins as an example of that. If I showed you the raw data, you would see the correlation between what they told us the design win was going to be, what they told us they were going to introduce it here, ramp up to here, ramp down to here in this time, versus what they actually ordered. You'd see quite a scatter plot. If you add them all together, however, the design win, massive design win data looks very good. The crowd is smarter than any individual in the crowd. OEM A is optimistic, OEM B is pessimistic. It averages out.
Yeah, and also I want to add the OEM related information you're referring to is actually incorporated partially in the field forecasts that come back from the field, because that's the customer basically, right?
Well, but there's another interesting part of that is that the people who you're making the design win with are a different group of people at the OEM that are eventually going to order the product. So, and the field sales guys are talking to both of them. So you get an interesting. There's a whole interesting study just in that question.
Okay, very good question. The question is whether the different leading indicators are truly independent. Now, the uncertainty in the leading indicator are basically coming from random fitting error from the nonlinear curve fitting. So the randomness itself, in other words, these distributions that I'm drawing there, are independent simply because they are random fitting error. So the theorem only rely on the fact that those fitting error themselves are independent. So because of that, we can reduce the variance regardless. Yes, that's a very good question. I think it's mostly for logistic convenience. In the implementation, we actually started with 10, and then we basically reduced it to 5. And because basically, although there are 29, but they all belong to roughly 3 families in terms of the shape and form they are. And so actually there is a point of diminishing return in terms of how many you use. As a matter of fact, when you use 29 versus use 5 is a relatively small difference that we see. So for implementation, it's just more efficient to do it that way.
Well,
repeat the question.
The question is, do the forecast analysts use this tool exclusively? Is that the question? Well, for those 9 products, any decision support tool we've ever implemented in Intel, particularly in this case where we're forecasting demand and starting work into factories, is an incremental acceptance process. That's why we ran it for so long in parallel. It takes the analysts a lot of time to see that we haven't just been lucky the first month or lucky the first 3 months that this thing actually works. So my answer to you is it's a ramp. They're using it more and more. And in fact, using it, again, as with any decision tool we've implemented at Intel, using it in ways that we hadn't thought of. It was originally meant for that 1-month forecasting process. Well, guess what? Forecasting questions come up in the middle of the month. The vice president asks, well, what if the competition does this and we do this? So it gets used in lots of different ways, and more over the course of time. Well, the historical data integrity was quite good. We keep quite good records on what we sell and who we sell it to and when and in fact, pretty good records on when they ordered it, when they changed it again, when they actually took it. So the historical data that we had here was pretty good. But again, forecasting the future, how good are the estimates from the field guys? Well, pretty good. Perfect? No. How good are the design wins? No. That's the point of combining the leading indicators to get to see, I guess I hadn't thought of this before, kind of a wisdom of crowds of leading indicators. If you take enough of them, and they're debiased as much as they can be, and you fold them together, you get an even greater debiasing. The biases cancel.
Right. I guess I would add that is one of the main point of the approach, is that it's the more leading indicator you use, and as long as you go through the process over time to make sure they are unbiased, then we can take a lot of very noisy data as long as they are unbiased. And actually, the more you use, the more the variance will reduce. And I guess my analogy is, it's like cooking soup, right? The more ingredient you throw in, the better the taste is.
Thank you.